All right, now we're recording. What? As soon as I start recording, you told me to stop? Oh, okay, thanks. So we're doing the lab today. Basically, there's this underground pipeline that is having to hit these various spots, and we need to minimize costs. And so the idea is that a lot of these numbers are like given to us, right? But we need to know. I think we're moving the W, X, Y, Z. Let me just verify. Yeah, see, we're finding what W, X, Y, and Z are, but we have everything else. So the only values we want are these four. Cool? Cool. Seems easy enough. Well, they cost different amounts for each one of these stretches. And so you would think easy, just go all the way down straight across. But that's not efficient enough. It's also not good to go straight across and down. So we got to do all this intermediate in the middle stuff. Blah, blah, blah. I think the picture's way better. And again, we have dollars in A, B, C, and D. And those are values we also have. So let me kind of like do a protograph of this thing. We have right here, 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 there, and then like way over here, right? A, B, C, D, E. The pipeline here costs like a dollar amount of little a, and this is a dollar amount of little b, little c, and then this is dollar amount of little d. This is W. Nope, be careful, Chad. Be careful. I have to make a point about this here in a second. The distance here is W, X, Y, and Z. Okay, and we're trying to find the W, X, Y, Z stuff. So the thing is that this I, J, and K are actual Y values. They're not distances. And that's going to be the problem. Notice that these W, X, Y, Zs are distances. They're different. And that's what's going to throw us off if we don't see that here, okay? Like the distance here, this little distance, is actually I minus J, I believe. Is that correct? Right? Like, let's just say like this was at a 10 and this was at 5. Right? So to find the distance, I would just subtract them. Right? This distance here is J minus K. And then this distance here is just K, isn't it? Right? So then when I need to find these straight line distances, I'm going to have to use these values in here instead. So that seems fun. But that'll be fine. Okay, so let's get like how much distance we're going to need for each one of these and costs, and it's Lagrange multipliers and all that stuff. Okay, so we're trying to minimize cost. So cost, let's find the total cost function. I'm going to start with this guy up here. I need the distance from A to B, and I'm going to put that in like simpleton terms, I guess. We got AB distance, and then I'm going to multiply it by little a dollars, right? Plus, I got my BC distance times little b dollars, my CD distance times little c dollars, and then finally DE distance times little d dollars. And I'm wanting to minimize this. Minimize. Is that looking good so far? I put vector, but I meant distance. It's the same thing, right? Magnitude, I guess. It would just start looking really meh eventually. I think there was a constraint though. Isn't there like a constraint that we have? Oh, right, we have some of these values. Those are kind of like our constraints here. So we'll get to that as we keep going. What is R? Oh, right here. Do you see this? Total, oh, I can't highlight it. Okay, well, here it is. Wx plus, so W plus X plus Y plus Z equals R. The total length there is 100. So that's going to be our constraint here in a second. So that's an easy one. We'll figure that out later. Let's actually like expand all this stuff. So I want the distance from A to B. How do I find distance? Okay. But it's a diagonal. I'm not wanting the vector. See, I want like the magnitude of the vector, I guess. I mean, without making it junky. Yeah, Pythagorean theorem. Exactly. So here we go. Square root of, I need the x distance and then the y distance. The x distance here is w squared. And then the y distance is I minus j squared. And then again, all this times little a. I'm going to put that little a in the front, because it's just a number. Little b times, yet again, here we go. I've got my x distance. And now I've got j minus k. Yeah, I think I did my key a little bit wrong. But we're going to do this correctly, and that's fine. And then finally, we got y squared. And I got a k. I'm going to go ahead and just do this here, if that's okay. Hold on. And then finally, I got my d distance times, what's my distance here of this last one? Just z. Do I have some of these numbers? Like I minus j? Yes. Yeah. I got the k's and all that stuff, so I can at least start putting some of these numbers in. So we got 50. I got w squared, 30 squared, 30. Yeah, I'm just putting them in, right? 10, 20, 20 again, and then d is 15 times z. And again, this is my minimum. I'm going to minimize that thing, I guess you can say. That looks pretty nasty. Good thing we have another equation. So from way up here again, that was this wx plus y plus z equals r. And so this is great. This is my cost. And then I guess, I don't know what this would be, like my total distance or something. Doesn't really matter. X plus y plus, it's w, isn't it? Sorry, let me start over. W plus x plus y plus z is equal to 100. And this is our constraint. This is our constraint. And so when I start doing this Lagrange multiplier stuff, this should be my f, and this will be my g. And basically, I just do the grad f is equal to lambda grad g stuff. All right, there's your lab. See you later. No. What? It actually gets really sticky, so I want to go do the first one, and then basically you repeat the process. Hi, I'm glad you're here. Yeah, we're doing the lab. And so can I just real quick recap with you? So we're trying to minimize the amount of money that we're spending on all this. There's minimize the cost. And each one of these distances costs a different amount, all this, numbers down here. And so I have to find each individual distance and then multiply it by its dollars. So distance times dollars, distance times dollars, distance times dollars, distance times dollars. That's my total cost. And then I have this other formula from up there, and that's my constraint. Now we're going to do Lagrange. And there, now you're all caught up. Cool? Cool. Okay, awesome. All right, so yeah, grad F. Okay, hold on. Before we do it, there is some good points, right? Because each one of these letters is like has its own plus sign, I guess, in a way. So right, no product rule essentially. You know what I mean? It's just that one derivative, although crazy, not too bad in the end. So yeah, let's do some grad F. So I'm going to look at the W side of things, this derivative here. See, I have a 1/2 power. So I'm going to bring that 1/2 to the front, leave the inside alone. What's 30 squared? 900, thank you. And now is it 900 or is it 9,000? I am going to verify, okay? That's funny. And then I have to take the derivative of the inside, right? 2w. That, and then all the rest for, again, this grad, we're doing w, there's nothing else. Like, that was it. Exactly. Right. So what I'm going to do is I'm going to simplify this right now so that I can basically just tack in the other ones as we go. For instance, the half and the 2 are going to cancel, right? That everyone's going to have a half, everyone's going to have a 2. The W is on the top, and this 50 is on the top. So whatever number we had, we'll put a number or a letter next to it, and then in the bottom, we'll put the square root of the original. Isn't that just it? So when I go and do the next one, it should just be a copy paste. Like, what was the number in the front? And then we're dealing with x, and then I just put that same square root in the bottom. That's 100 down there. 20y, repeat, 400. And then the last one's different, isn't it? Just 15. Just 15. My grad G is actually super easy, and that's why I want not much room for it, because it doesn't really matter. I'm looking right here at these guys. What's my derivative in terms of W? 1. And the X? 1, 1, 1, 1, yeah. So all this is equal to lambda times 1, 1, 1, 1. I'm going to pause on this right quick. This is like the pause point. I always start really big and write really tiny in the end. I'm so sorry. How about I do this and this and that? It's a little bit better. Okay, there we go. So this is the pause point because I ran out of paper. We're getting somewhere. Could I solve for something right now? Is there like an obvious thing I can do? Maybe. But isn't there like a... Okay, how about this? It's not in a nice format. Let me simplify it, I guess. I don't want to like go too far here. Is it going to let me draw? Okay, good. Okay, so I'm just going to remember the numbers. 50, 30, 20, 15, right? So 50, and that was a W. And I'm going to like do more math here in a minute. So I'm just copying it because we need to copy it eventually. But you have it written down. I'm about to give you the answer, but I wanted to see if you catch it first. Oh, no, that's a 400. Then that was a 15, right? I'm going to distribute the lambda. Hope you don't mind. I know, it's stupid. Yeah, do you see it? Look. Yeah. Oh, right. Basically I know that lambda's 15 for sure, like 100%. And so for the others, I could just say this dude equals 15, this dude equals 15, this dude equals 15, right? Go ahead. Like this vector equals that vector?
Right, and so since we have just a number there, we know that. Okay, that makes sense.
Cool. If I have this, couldn't I just solve for W eventually? Yeah. If I like, you know what? I'm gonna go ahead and cheat. I mean, it's a lab. It doesn't matter, right? Let me get some Desmos out here. So we had, was it 50 divided, and we got to use X, right? That way we can solve for it. And then we new. Yeah, look. And I know that it's not perfect, but like we can get a number. I know I'm not clicking on it. You know how to do this, right? You remember you change it to a minus? Right. So that I just gave you the answer. So oh my goodness, there's the answer. But like you can see how we can do this for all of them now, right? Because they're all equal to 15 apparently. Cool. So like the bigger goal, I'm done. I can't actually give you any more because then I'd give it away. The bigger goal was I needed to do this derivative thingy, Lagrange. After that, everything was like super easy because the constraint was super easy, right? So that's a good thing. Right. Well, that's why we do this together, this part, right? Where's my stuff? I have my lab somewhere. I want to go back to it. So now that you saw what to do, let me just say, like, what's the answer for this one? It says, what's W, right? You would put it in. What's X? What's Y? What's Z? And then it says, blah, 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 and you would talk about it, right? That's a talk about it. It's always 4 questions and a talk about it. So full sentences, blah, 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 whatever you do. Cool? That was it. That's basically the lab. So not too bad. But that's why we come here to learn about how to set it up, right? Set it up this way, blah, blah, done. Cool? And next semester, there'll be different numbers. So whoever's watching this now, you know now they're different. And watch me, I'm going to just forget. Okay. Any questions, though? Are we cool with this? You good with the setup? Good with the process? Where's my stuff? Cool? Cool? Okay, good. Okay, I'm going to leave it to you then. All right. Now on the fun topics. Yeah. Wait, no, not this. The fun topic is this one, but we have to do this one first. I'm just going to remind you the formula that we were doing last time. It's really no different than what we already were doing. I know y'all are getting stuff out. I'm going to just write the formula. Double integral of f over double integral of 1. And that's your formula, I guess you can say, for the average. If you look at this one, I think it's too easy. Why would Chad say that this one's too easy? Yeah, sure. The X's and Y's. What's so special about those guys? They're all numbers. They're all numbers. Didn't we go through this whole thing about like letters and functions and lines and stuff like that yesterday? And now they're just numbers. It's like, boo, it's too easy. Anyways, so I want to split these up. I'm gonna, if you don't mind, I'm gonna be not mathy. I'm gonna say top and bottom, because it just makes it a little bit easier to write. So I'm gonna say top. We're gonna do the top, and then we're gonna do the bottom, and everything will be happy. So help me set it up a little bit. What do I put on the inside of my double integral here? Too easy. I'm going to do dy dx. What would I put for my limits? They're making it too easy. It's somewhere in all those pages, isn't it? I'm on page 88. I don't know if they're numbered or not. Oh, they're not. Sorry. Yeah, 15.3. Yeah. It's actually such a tiny section. There's only 2 questions in this whole section. So there's, yeah, it's like, it's a continuation of the last one. There are only 2 questions. Yeah. Cool? Okay, cool. And then, yeah, we'll do the other stuff here in a little bit. But yeah, doing the top is going to be a little bit longer than the other one. I need to integrate in terms of y. What would I put next to my x squared? Yeah, x squared y. And the y squared goes to a. Very good. Very good. 0 to 3. 0 would cancel everything, so we're just going to plug in a 3. You're right. That makes it easy. And then I have to integrate for x. Straight up. Again, the 0 is going to cancel everything. Oh. 450. Thank you. It's the hardest part was arithmetic. Yes. I'm gonna chill out here for a second. The main thing is that because it's all numbers for my integral, this is super easy, right? Yesterday we had like a line occasionally, or we had like a little function doodad. Although not super difficult, it was just a little bit more time consuming. But I want to see if you can catch the trick for the bottom part, because you don't have to actually do any math for this. And I'm gonna go ahead. Yeah, no, I agree. That's all fine and dandy, but I just want you to give me the answer right now. I don't want you to do. Yeah. How did you know? Wow, that was a long thing. Well, 3 times 3 is 9. I mean, if you think about it, what's going on is we have 1, 2, 3, 1, 2, 3, and so then this region is what I'm trying to find the area of, right? So what's the area of a 3 by 3 square? It's 9, right? 3 times 3. 3 squared, exactly, because it's a square. Very good. So like being silly is fine. I just wanted to, show off a little bit. Because we have the top and the bottom, I can put it back together. So then my top and my bottom. Hold on. It's 6. Is it 6? It's because I already looked at the answer, right? There you go. Because 9 times 6 is 54. I hope not. I don't think so. Yeah, that would be sad. Man, that feels just like 14.7, right? Dang.
I'm still working on that copy.
I know. Okay, but overall, not too bad. Okay, keep it easy, basic stuff, right? And now we're finally done with that. So we'll come back to this average formula later when we're doing moments of inertia. But for right now, forget about it. It's great. All right, now on to some fun stuff. This is the actual, like, the first jump into the advanced side of Calculus 3. You'll be using this throughout the entire rest of the course, 100% sure. Okay? I'm not saying every problem, but I'm going to say probably 50% of the problems will be right here, right now, what you're seeing. So this is A stands for area. You can find the area using this new formula. And I'm going to even give you the other formula that we've been using is this one right here. Or if you want to be more explicit, it's dy dx. So these are both rectangular. And that's what we've been doing for a while. I didn't spell it right. Rectangular. It's like rectangle glue. Rectangular. But this is polar. And we've seen polar before in pre-cal and cal 2. So when I write these formulas, you're going to be so super familiar with them. You've memorized these dudes. Oh, okay. Well, that's why we're writing them down again, because these are so super important. Maybe. But this is where it's really kicking up a notch. This is the for real stuff. Those 4 formulas you will use every day in this class going forward. I mean, it's just going to happen. And then what I'm going to do is add more to it later. So, but these are the ones from pre-cal, and we're going to use them today many times as a reminder. So why go polar? Why can't I just do dy dx for everything, right? I know you're wondering. Because sometimes the integrals are really tough, and that the next one's coming up, I'll show you, they just don't make a lot of sense. Then we change it to this, and it's like, oh, that's easy. At least that's the hope. Okay, so it makes things easier once in a while. Do y'all have? I'm gonna wait for the formulas. I know you're writing. I'm gonna wait because they're very important. This is like key critical point. Gotta have these formulas. Okay, you're good. You set your pin now. We're good. Okay. So, oh, they even have some of them right here. And yeah, they talk about it. See, that's the rectangular, that's the polar. Just before I keep going, notice that there's an R here, and that was a 1, right? So R dr d theta is the requirement. I almost like to say that R is required. R required, right? So R is required. Just a little like side note, we'll be seeing that as we go. See, he's just hanging out there. If you forget him, it will be wrong. You have to include him in that format. So literally, dy dx turns into r dr d theta. Okay, you have to have that r required, r required, r required, r required. Okay, so this is a perfect example. They say, hey, go ahead and integrate. And you know, I don't mind integrating this. We just did this a minute ago, didn't we? With the average one. But then we have to plug that dude in. You see, like if I did this rectangular form, I'd have to plug this guy in. He's not just a number anymore. It makes it difficult. And then the next step would be difficult. And the next step would be difficult. And it's just like, why am I doing all this? When in polar form, it might be easier. At least I hope so. So we're going to convert. And what I want to convert first is this right here. That's the main function stuff. Again, this is all pre-calc. This is all pre-calculus right here. So I'm saying this turns into, and we have to figure it out in polar form. And what do you think is your guess? R squared indeed. There it is. So you put R cubed for your answer. What? Again, they're trying to trick you. Watch out big time. Because I'm going to erase this a little bit here because it's in the way now. You see how they have just R dr d theta? But I have to have a required R. Ding dong. So in a way, what I said is it's R squared times an R. So let me just make sure that you're seeing this. I'm saying this dy dx business is R squared always, and then r dr d theta. You see, your conversion is perfect, but they wanted more. Okay? Be careful. Be careful. It's just one of those kind of I gotcha moments. It's just a gotcha moment. The math was fine. They're just trying to get you. Okay, so watch out for that. You're like, man, I got it right. I know I got it right. And then it's like, what's the difference between these two? And it's going to be the stupid little R. Are we okay with that? You see when I'm talking? Okay. Yeah. So again, the conversion's perfect. They just want you to include that. So that's why it's R cubed. R cubed. All right. Now that we did that, the rest is interesting. Like that was the easy part. Now we have to like figure out what they're talking about right here, and then we're going to convert it into polar. And this is where we're going to start graphing a lot. So this is an x equals, and this is a y equals. I'm saying that x is equal to the square root of blah, 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 blah. First off, are you good at graphing x equals? Oh, you're getting better at it. Okay, well, let's take it back a year or two. Is that an easy thing to graph? No, it's not. We don't think x equals. We think y equals, right? So that's already not cool. Let's simplify this. What can I do to make it easier? Yeah, that might be a little better. What else could I do? Could I move my x and y over to the other side, maybe? in a way here, what I just created was a circle. Very good. That's a circle. I even circled it. So we're talking about a circle. And you see how that's going to be cool. It's very useful in polar form. That's why polar is going to be way awesome here in this case. We're talking a circle. Yes, yes. Um, I suspect it from right here because there's a square root of a square. That's a suspicion. But I don't know if I would say every time. I know the inside looks really pretty. That one looks a very pretty conversion, right? So yeah, this one's kind of more obvious than others. Sometime like they're gonna like here, just scrolling ahead. This one does not look as obvious. Like this one here, I would just do rectangular. I don't know why they force you to do this, because this is gonna be ugly. So yeah, but we have to do it for MyMathLab because that's what they're doing. So we have a circle, and its radius is 6 radius. Okay, okay. Let's figure this out. It says also we got y equals 6. So let me start graphing this in a different color. So y equals 6 is this guy. So I have a line like that. I have this circle thing. And then I got y equals 0 and x equals 0. So y equals 0 and x equals 0. Given that I have all these constraints, what quadrant do you think I'm in? Probably the first quadrant. Another indicator is that this right here is a positive square root, not a negative one. So it's kind of saying, hey, first quadrant is what it's trying to tell you. It's trying to say first quadrant. So we're looking at this little piece right here. And now I want to convert it into polar. So let's talk about what it means to do polar integrals. Did y'all do polar integrals at all in Cal 2?
No, actually.
Let's talk about it. Let's talk about it as if it's brand new. I want this chunk. This is the integral. What I'm going to do is I'm going to start from 0 radius, out until 6 radius. And then I'm going to do it again. 0 to 6, 0 to 6, 0 to 6, 0 to 6, 0 to 6. You see that my radius is constantly 0 to 6. So in a way here, when I go back and look at my answers, let me just get all this junk out the way. When I look at my answers, dr, so this is r, I'm going from 0 until 6. Exactly. I'm going from 0 to 6 every single time. Starting from 0, go out to 6. Go from 0 out to 6. So that one's an easy one. Yeah, please.
Just something kind of like I like when I try to figure this stuff out, write down just to make sure.
Yeah.
Can we also convert the x squared plus y squared to r squared and then take the square root of that to find r as well? When we're changing from x equals square root 36 minus y squared
You could. I don't know what you would use it for.
to find the r, find the radius, which is 6, because it's
Oh, you're looking at that 36.
Yeah.
So you see 6. Yeah. Yeah, I mean, essentially. And you can see these line up. I would say, yeah. Yeah. That's a yeah. Question mark? Yeah. Now, we're also wanting theta. Again, this is a theta. We're going from theta equals 0 to theta equals, so yeah, 90 degrees, right? And what, of course, you know they don't like to, yes. We're going right back to pre-cal again. No. Anyways, let's I'm gonna flash the answer so you can see. Yeah, we got it. See? Here we go. So now we need to find the actual value of this thing, and this is not too bad. It's not just finding the area of this quarter circle. I can't just say quarter circle area divided by 4, that kind of thing, because it's a variable density. So we have to, change it a little bit. But we have our new integral, and this should be easy. I'm gonna erase. Can I get some room? Is that okay? Okay. We don't need that anymore. We already converted. So I'm just going to rewrite it and start doing this thing. One other thing to note, looking at this, dr d theta, my limits are all numbers now. That's easy. That's a super easy thing. So we like that. I'm taking my integral in terms of r. What would I get? I agree. From 0 to 6. Plug in the 6. Simplified form. Okay, you're right. 6 to the 4th divided by 4. Wow, 324. Okay. We're going to do this cool awesomeness here in a minute, but what's my integral of 1? Theta. From 0 to pi over 2. Toss it in. We're done, right? Pi over 2. So I cut that in half. 162 pi. Is that the answer? Awesome. There we go. So super easy integral once we set it up. But kind of think of like the trade-off cost, right? How long did it take for me to convert it? Versus I could have probably just did it in rectangular, you know? Just a thought there. Okay. Cool. Yeah, fun times. I want to try something. I want to try something dirty. I want to try something dirty here in a second. Yeah. Are y'all okay with that? You good? Here we go. I'm gonna pull out some Desmos graphing, and I want to just do the integral without like any math. So yeah, avert your eyes. So you know the answer has a pi in it, and you could probably assume that looking at it, you know, polar form, all that stuff. And so we're going to just divide by pi here in a second and hopefully get the right answer. Oh, it's dx dy. Okay, so then I have to do the 1 over pi thing. Oh, too easy. I thought that it would at least like be a little bit more difficult, but apparently not. My goal was to show, which I failed by the way, my goal was to show that the rectangular version isn't always as accurate. 1 over pi. But apparently it was fine. I was hoping to get some like weird decimal or I don't know what's going on, blah, blah, blah. What is it? No, apparently it's fine. So either way. Okay. Well, I guess that's fine. Any questions on the conversion? Once we get that done, it's easy, right? So why would we convert this thing at all? What a pain in the... Because they want it done. Isn't that sad? I don't like that at all. In fact, I'm going to be so rebellious. I'm just going to go ahead and do this integral right now. And then I'm going to let y'all do that. No, how mean of you. So I'm going to integrate in terms of x, right? So we get what? I know. I do the same thing. Plugging in a y, you get 1/2 y squared. The 0 would cancel. When I integrate this, yeah, I'm being super lazy. Plugging this guy in, we get 8 over 6, which is 4 over 3. And we just did the entire integral without their help. I'm even going to go verify the answer here. Let me just flash it right quick. And yeah, 4 over 3, there it is. Well, that was a waste of our time. So like, and that's fine. It's sometimes, and again, going forward, if it's rectangular, do rectangular. There's no need to waste our time doing this polar stuff. Yeah, well, we have to here, yeah. I'm just like later, if they say just find the value, yeah, we just do whatever's best, Desmos. So, but like, okay, so that was not too bad, but let's start converting it. In fact, I want y'all to try to convert it. Okay, I know it's a little weird, but it actually is technically easier because look how like small that is. Now I'm going to relist it all out. I've got x equals y, x equals 0, y equals 2, y equals 0. At least like try to find the region. Draw a graph, convert it to polar form, blah, blah, blah. Tell me what you get in a minute. I like that. True. I like that. Very good. It's as if you've already seen the answer, but you probably didn't write it down. I'm not doubting you. You did good, of course. That's very good. Maybe, but draw a picture and imagine how we can use that. And this is good for you to kind of explore. Yeah, that's your thinking face. So much so he's not paying attention. Oh, why? Well, you had a good thinking face on. You know what I need to do? I need to control Z. I'm going to use a different color. Okay. I drew my picture. So my inside would be something like this. Did y'all get something kind of like that? Okay. Okay. Well, that's an interesting thing for polar. And that's okay. So let's think about how that would be polar. You know what? I'm gonna scroll a little. I'm gonna use this down here. So we have this zone here. Okay, here we go. Aha, There you go. You got it. That was very good. Good analysis. So I'm starting from 0 going out to 2. But then I'm going from 0 out to like my radius would be not that. Oh, actually it would not be 2. Wouldn't this go out to 2 square root of 2? Right? Because it's like diagonal. And then it goes out to 2.1 and 2.01 and 2.001 and then finally just 2.0 essentially. So yeah, my radius is changing, but it's always starting at 0. And I could tell you what part of the arc that I'm on. See, if you imagine this being a unit circle of some kind, right? What angles am I working with? Yeah, 45 all the way to 90, right? So those are going to be my angles, at least. So let's start to set this thing up. I know they put 0 and whatever already. I don't grr. There we go. Okay, so let's fill in some of the pieces. Yes, we already know that's a 0, and we already know that's a pi over 4. What does the pi over 4 mean, though? Yep, that's that 45 degrees. Therefore, I already wrote down the answer. So therefore, if I go in the 90, I should have right here. So there's my 90 and 45 that we were just talking about. The only thing that's a little weird is going to be this guy. We'll get back to this in a minute. I don't really care. So this is an R equals, and it's going to be something, right? It's this weird flat line thingy. Do you remember how to draw a flat line, a straight line in polar form? No? What? You never? Oh no, surely. It's secant. Secant is a straight line or cosecant, either way. I know that's so strange, but yeah, if you like here, I'll show you. Let's go to Desmos graphing right quick. I'm not trying to quiz you on like, do you know your polar region? But if you did secant theta, home, see? Or if you did cosecant theta, see? One of these, right? It'll be something like that here in a second. I'm saying like if you kind of know what you're looking at, you can just pop get it. Because it's like, oh, I know a flat line. It's cosecant or secant, and then you could just change it, right? So this will be like a 2 or a 3 or a 4 or a 5. Very simple, right? So if you know what to look for, right? What would be my answer technically, like immediately? Yeah, exactly. Well, I don't need that anymore. And yeah, you're right. Yeah. Oh, well, there's the answer. Right, and 1 over sine is cosecant, exactly. So yeah, we just found that this was a 2 cosecant of theta. But let's just say I didn't know that. How would I derive it? How would I know how to get to that looking at this stuff here? So I have y equals 2. I mean, that's that line right here that we're looking at, right? Y equals 2. So let's convert that part. What was y equal to again? X, true. R sine theta is the polar form, yes. It is equal to 2. And I need R equals. So what do I do with this thing here? I divide it. There you go. R is equal to 2 over sine, which is what they had. And that's true too. Tangent equals 1 at 45 degrees. And that's how they got that value. So in a way, when we're looking back, that was an excellent point. Sorry, I probably shouldn't erase that. I'm sorry. It was R sine theta is equal to 2, and then we're just taking that and dividing it to the other side. So looking at the region, I'm saying, hey, which of these equations gives me that flat line? Which of them gave me the 45 degree line? Which of them gave me the upper line? Right? Couldn't I have taken this one? R cosine theta is equal to 0. Well, no, because I need to say I need to solve for R equals still. No, it would be a theta. We're solving for theta. So like in a way, I'm like, well, how do I get this whole thing equal to 0? R can equal 0, but also what can I do here to make it equal 0? That's 90. And that's the point. That's how we got the 90 over there. Like, in a way, you're using each one of these, in its own polar form to get some numbers out of it. Or you could just say, oh, I know a flat line. So going forward, that'll be a quicker way, right? Now, what's on the inside? This one should be pretty easy. Very good, because originally it was just an x, r cosine theta, but we needed. Oh yes, you should keep it separate. You should, because you'll go back and say, how did I get r squared? Because this is what was required. And then that was the x. Exactly. 100% true. Okay. We got 8 more minutes. I know it's cold in here. I don't know why they changed the temperature. I mean, it's like, oh, well, it's feeling a little warm outside. Blast. All right, pause on this one. It's like, bro, I can't do that in 8 minutes. Would you want to do this in rectangular? Looks pretty gross, right? Like, the derivative ln is 1 over stuff, and then you got its little derivative thingies. Or, I'm sorry, derivative. Did I just say derivative? I'm doing it too. I'm doing it too. Right. So the goal here is that it's all messy and it's gross, and I don't want to do it. But you can see that we got the square root of the squares, and look, the 49 and the 7 match up. So what we talking about right here is definitely a circle. Definitely that's a circle somehow. So I think that we're going to get some really easy numbers here. 7. Yeah. Yeah. Now, they have a 0 down here, which kind of scares me, because if you notice, we're going -7 to 7. We're going negative square root to the positive square root. I mean, in my mind, that was like a full circle. So actually, yeah, that's fine. 0 until full circle would be 2 pi, full circle. Just kind of looking at it, just kind of looking at it. And those are both numbers. We're really close. Put an r over here, and now I just got to convert this mess into this thing. Did I make that clear enough? Yeah, I don't know. But yeah, I do. We're going to do the math, of course. But like, in a way, and we're going to come back and do this again. I just want to like say, if you see it, you could do it, But let's go back. We'll do that part again later. I want to focus on just finishing this part up, and we'll talk about it again next time. So yeah, we got ln of junk. Well, don't I have this x squared plus y squared is equal to r squared? Very good. And we still have a plus 1 in there. And we have an r on the outside, dr d theta. Yeah? I think so. I don't know what else to do. I mean, do you know what ln in polar form would be? Me neither. But what is the integral of ln? Flip. No, that's the derivative, see? So flip. I can't remember. It's like x plus x ln x or something like that. I don't know. It's weird. It's complicated. It would only get crazy stupid over all this stuff. But we have u sub here. If we do an integral of this thing, I can do u sub because of the outside r. Bam. It makes it so much better. So we're going to do that here in just a second. But let me just, are we cool with the conversion of that thing? Let's talk one more time about the conversion of the outside, because I did skip over it. I just said, hey, look. So I'm looking at the square root, and we're saying, hey, that's that arc here, and we got the negative 1 here, and they're saying we're going from -7 to +7. It's just basically a full circle. And you can verify if you want to by saying y equals this, and then you could square root both sides, or square both sides, etc. So I want my r to go from 0 out to 7, 0 to 0 to all the way every time, 0 to 7, all the way across. And how much arc did we have? How much theta? 2 pi. Hi. Did you get a haircut? Looks good. So yeah, if we're going from 0 to 7, all the way from 0 to 2 pi. We'll do a lot more on this later. We got 4 minutes. I'm going to figure it out. But we're going to... Do you want me to cover it next time? Oh, okay. Okay. Okay, then we'll do it next time as well. Awesome. But look, can I keep going? Thanks. So we got this ln thing I got to do. Like, let's just focus on what's the ln of this junk, right? If I can get past the first one, I bet I can like go further, right? Because I mean, I got all this other stuff here. I don't really care. But what's this guy? So let's do the u thing. You no. Bad Chad. Okay, and then dr would be du over this stuff. So when I go back and do this again, it'll be integral of the ln of u times r, and then yes, du over 2r, and then my r's are going to cancel. So now I got integral ln of u du. Oh, and there's a 1/2. Definitely. Okay. Let's pause on that. So blah, 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 blah. I got down to an integral of ln, but it's just that's it. Just integral ln, and that's it, right? So now we go back to the formulas, which I believe, I'm trying to remember here, it'll be u plus u ln of u. Are you confirming that with your head nod?
I was gonna look it up.
I wish I would have brought my formula book. I think that's what it is, though. So then I'm going to say u plus u times ln of u. And then I'm going from 0 to 7. No. I'm going from r equals 0 to r equals 7. Whew, man. So much complicated stuff. Of course, the u, I'm going to go back and plug it all in. So then I got r squared plus 1 plus r squared plus 1 times ln of r squared plus 1 from 0 to 7. All right, that's easy now. Yeah, it should be. Yeah, Desmos, I'm thinking. Did I mess it up?
It's integral is x ln x minus x plus c.
Minus x. Mm.
To be fair, that was really close. You just have a plus or a minus sign should be.
Nah, it's not good enough. Erase everything. Ugh. Bad Chad. Thinking that he's all cool and stuff. That's not good at all. Bad Chad. Bad Chad. R squared plus 1 ln r squared plus 1 minus r squared minus 1 since I distribute. I'm going to just do some of this math. 7 squared is 49, so we got a 50. ln of 50. What? Did I mess up already? Yes. And then I got a negative 50. And then yes, minus, when I plug in a 0, I'll get 1. ln of 1 is 0. Plug in this one in, and I got a 1. So I essentially got, right, negative of the negative 1 will be a positive 1. Boy. Why do I always write so tiny at the end? Bad Chad again.
Hey Chad, you want to know what the best part about it being in this format is?
Huh.
All you do is just slap the data on, you plug your numbers, throw it in Desmos, and you're good.
Anyways, you're really close to a concept that I was gonna say. This is the I know we're 1 minute over now. I'm so sorry, but y'all are happy. I'm gonna just take the integral here. Remember that this was 0 to 2 pi, and there's no other variables, nothing else left. And so we do this thing that's called the 2 pi slide. Yeah, 2 pi slide. That's what you were talking about. There's nothing else to hinder us. What's the integral of all that number in terms of theta? Theta. What do I do with the 2 pi? You plug it in. So you say times 2 pi. That's called the 2 pi slide. At least, okay, Professor Lyles named it that. And now he's a dean. So now you know it's true. This is the answer. But I want to see what they got for the answer. Oh, okay, look. Right, because I did the 50 and then the 1. Where? Boom! All right, we'll come back and revisit the limits, though, okay? Yeah, because I want to talk more about limits. I love the limits. Thank you, guys. See y'all later.